before we talk about our new data structure of the day, let's talk about the competition, what we've come up with so far for implementing a set. So we have a set here that's a contains operation and an insert operation, and in this case I'm using an ordered linked list like we did before we invented trees. So if we wanted to do the contains operation or insert, consider what is the worst case time in big theta n. So think about that for a moment. Okay, so you should figure out, hopefully it should be fairly familiar, that these are both big theta n in the worst case. So if I have, for example, contains g, I have to look through the whole list. If I do insert h, I have to go through the whole list to find the spot to put it. Okay? So that's one approach. One that we detailed last time was the so-called bushy binary search tree. So here again we have a contains operation and an insert operation, and inside we have this binary tree. So if I wanted to do a contains operation, say contains r, the worst case is I have to go all the way through the tree, and in that case, if it's bushy, the height of a tree we discussed is log n. Likewise, insert in the absolute worst case, as long as the tree is bushy, the height of the tree is log n again, so we have to, say we're inserting z prime, which goes over here, then I would have to go through all the way through the list and insert the new z prime at the bottom. And so a bushy BST, the contains operations should be big theta log n in the worst case, insert should be big theta log n, and we have a few caveats. So unlike some ideal data structure, the bushy BST has certain things we have to worry about. One, our items have to be comparable. So in order to know where to put something in a tree, we need to be able to say, is it to the left or to the right? Is it smaller or larger? So that's actually a limitation, because sometimes you might want to store a set of items which are not comparable. Another major issue is that maintaining bushiness is non-trivial. So one approach is to use something like a 2-3 or 2-3-4 tree, or we could use something like a red-black tree, which are a little more challenging, and basically it's hard, okay, to keep things bushy. And then there's also this other question, which is, okay, well we got log n here, but there are functions that grow more slowly than log n. For example, the constant or log n or whatever. And so the question is, could we somehow do better, build a set whose runtimes are better than log n? Now I'll make a note that log is actually very good, right? We shouldn't be like, oh god, we have to wait for this log thing. Because even if you have a billion items, which is about as big as a tree as you could build in Java without resorting to strange measures, it would yield a tree height of only 30, right? So 30 is not bad. If I have to walk down 30 levels of a tree to get something, I mean, it's worse than one level, but it's still not bad. It's not like a billion, right? So log is very fast, but it is interesting to wonder whether we can do faster. So I'm going to introduce a new and strange idea, which is to use an array for implementing a set. And why strange? Well, it's going to seem like it's not very good, and it won't be at first. Now I bring up arrays because so far, at the beginning of the class, we had this interesting dichotomy between linked data structures versus arrays. We had array dex, linked list dex. But now we have this array. Or now I want to consider what happens if we use an array instead of a linked data structure. So consider, what would be, and let's say it's unordered, right? It can be in any order. What would be the runtime for contains, and what would be the runtime for insert? Okay. So I believe that contains should be theta n. If I want to know if x is in a list, I have to scan through the whole thing. And if I want to insert something, even though it's unordered, I really don't want 2 copies of something. I mean, I guess if you're willing to allow multiple copies, you could make it quicker. But if I want to insert something into my set, say j, well, I need to make sure that first that j is not already there, okay? Rather than just sticking it at the front. Otherwise, I'm wasting memory. So an unordered array will be runtimes big theta n in the worst case. Okay. So I'll make a note here, which is that unordered arrays don't seem to be any kind of improvement, right? They actually seem kind of terrible. And you might say, okay, what if we do an ordered array? But it turns out those won't be very good either. They'll still have a linear time operation. But a third type of array could be good. Okay. Neither unordered nor ordered. I'm going to use a different type of array altogether. This might be a little peculiar, but you'll see it's very cool. The idea here is going to be to take advantage of the fact that computers can access any element of an array, no matter how large, in constant time. And we'll also make a note that all data is really just bits. Anything out there, any string, any song, anything, could be represented as bits. And so what that means is that, in principle, there's some way that I can use the data itself as an array index. Any data It's just a number. And so it could be used as an array index. And so what I'm going to do is I'm going to create an array of possibly very large size. And anytime I want to say, and I'll initially set every value to false, and anytime I want to add something to this array, I'm going to set the appropriate element to the array to true. So we'll start with integers because those are the simplest thing to imagine. So if I want to create a data indexed integer set, well, initially all of these things will be false. But when I insert something, let's say I insert 0, that means I'm going to go to position 0 and set this to true. When I insert 10, then I'm going to go to this position and set it to true. And so after a sequence of 4 inserts, I'll end up with this array. All falses, possibly a huge number of falses, but a few trues. Okay. Now there's some obvious downsides of this approach, right? Well, if we wanted to, for example, store all integers, we're going to have to need a really big array. Going to have to need, yep. And that means it's wasteful of memory. So if we wanted to support checking the presence of any positive integer, we'd need 2 billion booleans, right? So I need to, if I want to know if item number 1 billion, or sorry, if the number 1 billion is in the array, I'd need a billionth true or false. And then we also need some way to generalize beyond these positive integers. So negative numbers won't work, strings won't work, but we'll get there, okay? But what I want to point out is that this is very fast, right? Doing this insert operation, I just have to go to the appropriate element in the array and just set it to true. If I want to check if something's in the array, I just check if that spot is true or false. And because a computer can check any element in an array in constant time, it's going to be really fast. Okay? So what would the implementation look like for this thing? Well, it turns out it's actually really simple. When you create a data indexed integer set, we set an array of booleans, all to false, and we insert something or do contains, we're just setting booleans. And this is about the simplest data structure you can imagine, and it's also constant time for all operations. Look at them. Now, of course, 16 is not going to hold many integers, so we might increase it a little, and this will allow us to store any number up to 100,000. And as long as nobody tries to use an integer outside of those ranges, everything should be fine. And within these ranges, then we can say that the runtimes, in this case, are going to be big theta 1 for both contains and insert. So we've beaten bushy t's, bushy BSDs, and everything is faster. Right? Oh, sorry, everything is simpler.